we come to this position, inductivism, positivism. You all heard these names, inductivism, positivism. Probably, well, some of you will not be entirely clear, especially positivism. I mean, isn't being positive wonderful? Isn't that good? Well, if you talk about COVID being positive, it's not so good. So the word positive is somehow strange, right? Something the positive is negative and the negative is positive. What a strange world. Anyway, so one has to understand what's behind that term, and I'm going to tell you. So this position, positivism or inductivism, was developed in the 17th century by various authors in the context of the development of modern physics. So you may know that in the 17th century, modern physics was invented. And as always, when something completely new in the realm of the sciences is invented, there's usually always connected with it and at the same time developed a philosophy of it, because people wanted to understand what they were doing. Yes? Not quite. I'm coming back to it. Okay, I'm coming back to it. So, you find the same in antiquity when people started inventing science in ancient Greece. Then they also had a philosophy. It was not only the invention of that discipline, these disciplines that were invented there, but also people thought about, what are we doing here? And this is then a philosophy of science. And that's similar here, that it was invented by various authors in the context of the development of modern physics. So it's a position that was invented for physics, for the physics of the 17th century. Now, that may be good or it may be bad. It's just something one has to know. And if you think, oh, that's a wonderful position, then be careful. Can it really be applied to economics? Does it work there or doesn't it? Does it only work in the context of a physics, if it works, in the context of a physics of the 17th century? Does it work for the physics of the 20th century or the 21st century? Completely open. All right. So let's see. All right. So there is a basic idea of inductivism, and that's something important that one has to know when scientists speak about inductive procedures and that stuff. Then one has to understand what the basic idea of inductivism is. And that idea becomes relevant once you see that there is a distinction in science, an important distinction, namely between singular statements and general statements. Singular statements are about one fact. And general statements are, as the term says, about more facts. They are general, about all facts of one sort. So that's a difference, right, between singular statements and general statements. Singular statements, here's an example. The economic growth in Switzerland, the annual variation of GDP in percent, was 0.9% in 2015. That's a singular statement. So there is a singular fact, and that fact is the economic growth in Switzerland in 2015. So this is one fact. I mean, it's a complicated fact. It's aggregated and so on, but it's a singular fact here. So economic growth, that's a singular fact. The singular statements often express observable facts. Not really in economics directly, because it's difficult to say that the economic growth in Switzerland in 2015 was really observable in a direct sense. Well, you have lots of data you have to aggregate and blah, blah, blah. So, but if you look at the primitive or the simple physics of the 17th century, then this was exactly the case. So you investigated a gas and the pressure and the volume of the gas, and then you said, okay, I can really observe what is the volume of that gas, what is its pressure with an instrument. And then it's very simple that you have simple facts, but you can say these singular facts, singular statements, they express observable or measurable facts. In the case of economics, of course, it's a measurable fact, a singular fact. So that's one thing, the singular statements. In this case, it's easy to verify. And verify meaning here to confirm the truth of the statement. If it's observable especially, you observe or measure and then you know it, right? If you want to know what's the economic growth in Switzerland in 2015, you've got to measure it. So you're going to get, once you know what the definition of the gross domestic product is, then you know which data you need, and then you aggregate them, and then here you get the number, what the annual growth is, right? So this is comparatively easy. I mean, it's difficult enough. I mean, first you have to have a good definition of what the GDP is. Anyway, and this is, as I told you the last session, that there are value decisions in that, and it's not that easy, it's not that neutral. But anyway, once you said, okay, we work with this definition of the GDP, then I get this number, And it's comparatively easy then to verify, to be sure that it's true that the economic growth was 0.9%. That's comparatively easy in comparison to what comes next, right? It may be awfully difficult. So for instance, if you have to verify, it's also a singular statement that 65 million years ago, the dinosaurs were wiped out. This is a fact, right? A singular fact. The dinosaurs were wiped out. But to verify that, to show that this is true, it's quite complicated. But it's something else when I have a singular fact like what Hoyningen teaches today at the University of Zurich. Yeah, just look, here he stands and talks. And if he doesn't tell jokes, he's probably teaching. Okay, so it's comparatively easy to verify singular facts because you just have this one fact that you have to focus your attention on, and then you look what it is, and then you can make a statement. And it's much more difficult about general statements. And the point is that not only physics, but most sciences, not all sciences, most sciences and other academic disciplines don't want to stick to singular facts only. They want to articulate general statements, namely concerning laws, theories, general hypotheses, regularities, models. And of course, economics is no exception. History of economics wants to get at particular facts, right? What was the gross national product in France in 1614? This a historian of economics may want to know for some reason. But if you look at the other disciplines like physics or economics, usually you want to have general statements. And the problem is they cannot be verified in the same way as singular statement. Why? They typically refer to indefinitely many facts, right? That's the problem. So you have in these general statements, so if you make a general statement about the law of free fall, right, for instance, that's probably as far as you got in physics, and then you speak, of course, about all instances of free fall, all that have ever happened and all that will ever happen, right? And you speak about an infinity of different facts, and you make a general statement about them. Namely, for all of them, the law of free fall holds. And there's the question, wait a minute, how do you know? I mean, couldn't you be wrong? And that's apparently, no, obviously, quite different in difficulty in comparison to a singular statement, right? When I say this ball or this, well, I won't do it. This ball fell down and the velocity was this and the time was this. You measure it in period and it's comparatively easy. But when you speak about all possible cases of free fall, then wait a minute, how can I argue for that? I can only observe a few and then how do I generalize? So that's the problem here. So general statements cannot be verified in the same way as singular statement, but we need something else. And that means that in very noble terms, the epistemic status of general statements is problematic. Epistemic status meaning episteme is the Greek word for knowledge. So with respect, whether it's knowledge or not, it's more difficult to find out about general statements. And the point was that in the 17th century, there was, the idea was, and that is a comparatively new idea, that there is something like natural laws, namely general relations. And physics, the new physics from the 17th century, wanted to investigate and discover these new laws. Right? The concept of a natural law was new in the 17th century, it didn't exist before really. And therefore, this question of how do we verify our hypotheses about general laws? How can we do it? So, and the example is, I give you another example here, the so-called law of demand. As far as it is a law, well, it's a regularity. Anyway, when the price of a product decreases, its demand increases, ceteris paribus. Right? So this is a general statement. It doesn't mean when you go down to the Mensa and buy a cup of coffee, but it means, you know, in all markets under certain conditions, that regularity holds. And the question is then, how can it be confirmed as it applies to infinitely many cases? So how can you know that? I mean, you're talking about cases you've never seen. And the question is, how do you know that? I mean, how do you do that? This is not clairvoyance, but it's supposed to be science. So how do you do that? Okay. And in inductivism, and that's now where we come to this term also, in inductivism, it is believed that we gain general statements by what is called inductive generalization from confirmed singular statements. So in a way, and I give you some rules for that in a second, you start with a few cases and then somehow you generalize to all cases. That's of course risky, probably somehow anyway, but that's the basic idea. We cannot observe all cases, but if we cleverly look at a few cases, we may be able to generalize. And that kind of generalization is called inductivist, inductive generalization. That comes from the Greek word and translated into Latin, and then into English, it's inductive generalization. It means this concept of coming from a few cases and then going over to infinitely many cases. That's at least one way. And inductivism therefore states that in general scientific knowledge is gained in a two-step process, general science as opposed to singular scientific knowledge about singular facts. It's in a two-step process. And in the first step, you've got to get these singular cases, right? You carefully observe singular facts without any theoretical prejudice. There's sometimes the terminology, theory-free facts, right? You don't have a theory in the back of your mind, but you just look, what are the facts? And you don't project any theories in there, but you're just observing neutrally what is the case. And you articulate them in singular observation sentences, right? So you want to know something about gases, and then you just observe the gases in particular states, and you write it up. The gas was in this state, and that, and in that state. Okay. So that's the first step. You get at the singular facts, and that is comparatively, with the next step, easy. It may be very difficult still, but comparatively, it's comparatively easy. Reason being simple because you only have one fact. Well, the fact may be itself complicated, like the disappearance of the dinosaurs. That's a very complicated fact. But in other cases, especially in a very simple physics, as it was in the 17th century, it's very simple. It's very really easy. And also in some of the economic facts, some of them are really comparatively easy to get at. Right? Now, these facts are then often called data, or they are also called positive facts. And positive facts come from the Latin ponere. It means just they are somehow given and set, right? So the point is, and that is therefore the position is also called, any position that starts with positive facts is called positivism. So sometimes you hear scientists saying, look, I'm taking now a very positivistic procedure. And what they mean is then, I just collect some facts, right? And I start from the facts, and then I continue. So starting with a positive with facts is then often called positivism. And the idea of positivism then is that a science should start with the inductivist procedures. It should start with positive facts. And therefore, sometimes inductivism and positivism are used interchangeably, although they mean different things. Right? But they result in the same thing. You start with facts and you generalize. And that's the same in positivism or inductivism, but you have the stress, of course, on different facts about this procedure. So that's positive fact. That is where positive economics comes from. Right? This is only in economics. In the other sciences, you do not speak about a positive, for instance, in sociology. You have social philosophy and you have sociology, which is the same distinction as you have in positive economics and normative economics. But you do not speak about positive sociology, but then you speak about empirical or descriptive sociology. So in other fields, you use the adjective descriptive, right, or empirical to make the distinction to the normative part. Typically in sociology, if you talk about the normative part, people usually say social philosophy. Right? That this is meant then. In economics, the terminology is positive and normative. Normative is a wonderful term. Positive is potentially misleading, but this is history, and so we speak about positive economics. But now you can understand where it comes from. Now, okay. Inductivism. So we have the first step, we observe singular facts, and then we need the second step. We have to generalize from the data, the positive facts, to general hypotheses or laws or theories or models, whatever their terminology is very unclear. and very fuzzy. So, sometimes physicists speak about a model, then they about a theory, and about fundamental equations, and it's not a fixed terminology. So you shouldn't, when a scientist speaks or economist speaks about a model or hypothesis or a theory, you don't really know what he or she means. It's very fuzzy, but it doesn't make much harm as far as I can see. So you have to generalize from the data to the general hypothesis, and this step is called an inductive generalization. Right? That's the idea. It's a very particular kind of generalization, and it's called inductive from a few or some singular facts to the generalization. And it seems now that, of course, you can't do that just in every case, but there must be some conditions met that this inductive generalization works. And it seems to be allowed if the number of data is large. So don't generalize just from 3 or 4 data points usually, but you have a large number of data. If the data are gained under sufficiently varying conditions, so things have to change, you have a variation. If you have just a small sample of data, that may be misleading. And if none of the data contradicts the intended generalization, right? Under these conditions, you are allowed to generalize. What you see immediately that this is excessively vague, what I'm saying here, and this general, so to speak, philosophy of inductivism. I mean, what does it mean the number of data is large? I mean, sometimes it may be 15 data points, but it may be that you need 10 million data points, right? So it's completely unclear what that means. It really depends. It just, it must not be small. Yeah, very helpful, right? So this is really very, very, very vague. But if you talk on this abstract level about inductivism, it's clear you need something like that. It must not be too small. And also, the data are gained under sufficiently varying conditions. What the hell is that supposed to mean? Sufficiently, right? I mean, when is it sufficient to vary the data? I mean, what does that mean? So this is utterly vague, and that is, if we articulate that position in this abstract level, it has to be vague, and there is a fundamental vagueness that is a problem of inductivism. The question is whether that can be healed, but we come to the other positions and then we'll see what they do with that problem. So there is some vagueness inbuilt, but this is simply part of the idea. Right? And it seemed to work in the 17th century with the new physics. It worked. They worked under these inductive rules. And then you learn, what in a certain context large means, the number of data. And you learn what it means to sufficiently vary the conditions. And you get some experience. And then you say, yes, this is how I have to describe what I'm doing in science. And as I said, it worked in the 17th, 18th, and partly in the 19th century. So the physics that was produced in this way. There are, apart from this vagueness, various problems of inductivism, and I name only one that's very important, and that's also playing a role sometimes in economics, that there are examples that represent a fundamental problem of inductive generalizations. So, this procedure where I say, okay, let's have a few data points, or a large number of data points, and then we generalize, and that's a wonderful procedure. But there is a fundamental problem, and that problem I want to address now. Now, imagine, this is a rather cruel example, someone falling from the top of the Empire State Building and states, I fell 20 stories, now it's 40 stories, now it's 60 stories, now it's 80 stories, so I generalize inductively. No problem how many more stories will be coming. No problem, right? And there you see that doesn't seem to work very well. I think it's 100 stories or something, 110 Empire State Building. So then the fall is over. So you see that under these conditions, generalizing inductively, although it looks wonderful, I mean, varying conditions, 10, 20, 30, large number of data points, and still it doesn't work, right? So problems arise. Oh, here's another one, which is a little more technical. My measurement of the melting point of wax consistently gave the result of 54 degrees Celsius. So all wax will melt at 45% degrees Celsius. And probably if you're not a wax specialist, you will say, yeah, that's probably right. That's wonderful. There's a natural law of wax. Well, it isn't. Okay, so what's the problem? Now, the problem is that the general hypotheses in these examples are what can be called accidental generalizations. And an accidental generalization is a generalist statement that may be true, but true by accident, right? True by accident. Whoops. Yeah, no, that's good. True by accident. So the example for something being true by accident is, for instance, all the coins in my pocket are made of copper. That may be the case, right? Today, if I look in my Inductive, all are made of copper. But of course, everyone knows immediately that's an accident. I mean, there's no natural law or something, anything. I mean, there are different coins, and it happens to be that all of my coins are made of copper. So there are general statements. They are as general as other general statements, but they are true purely accidentally, or false purely accidentally, right? So they are there, and inductive generalizations don't work for these accidental generalizations. Because if you say, so I have 100 coins in my pocket, I take out 10 and 20 and 30 and 40, all of copper. And then you say, well, then clearly I can generalize. All of them are of copper. Of course you can't, because it's a pure accident. And the same is, it's a pure accident if you fall down the Empire State Building, and because it's 100 stories, that the first 80 stories is no problem. Right? Of course, yeah, but you can't generalize it because it's a pure accident. If it was only 20 stories, you'd realize earlier that you can't generalize. So it's a pure accident. So inductive generalization seems to work if it hits a natural law, namely a regularity apparently based in nature itself. So that's the way people speak. For instance, Galileo's law of free fall. So if you measure a few instances of Galileo's law of free fall, and then you generalize to the law, fine, that seems to work, right? Because you hit a law of nature, as people say, right? But it doesn't work if you generalize to something which is only accidentally true and not by nature itself. And that's the problem. So the problem of one of the core problematic aspects of inductive generalizations is they only work if you happen to hit upon something like a natural law, and not something like an accidental generalizations. They definitely don't work for the accidental generalizations. Definitely not. So what you need in order to use inductive procedures is somehow you must find out whether you're working on a generalization that's a natural law and not an accidental generalization, right? That you have to find out. And that's the problem that's behind here. And I give you examples. How to tell the difference. Right? What do I have to do? So in the cases I gave to you, you know from your knowledge, everyday knowledge and high school, you know that there's a law, free fall, and of course everyone knows you probably have never, ever in your life asked the question whether having all copper coins in your pocket is accidental or a generalization, but you see immediately that's accidental if that happens to be true. So how to tell the difference? And if you look at the two examples there, then you need more variations of the conditions that is necessary in order to see that the generalizations are not laws. So in the case of the falling 80 stories, you need more variations, namely you need 110 stories, and then you see, whoops, that's not general. And the same is with the case of wax. It happens to be the case that wax does not have a definite melting point. So it depends on the kind of wax that you are using. And I don't know the range there, but 54 is in that range. But there are other waxes that melt only at 58 and others at 49. So you see that not enough variation gives you the impression, I can generalize here the melting point of all kinds of wax, but as soon as you change the kinds of wax that you're using, then you see, oops, that's not true, right? So it was accidentally that all these samples that I measured the melting point, they all have 56 degrees, but it's a pure accident, right? If I had started with other samples of wax, I would have ended somewhere else. So the point is really that during the process, you must identify whether it looks like it's really a solid natural law-like thing or whether it's an accidental generalization. And that is something which is a deep problem in economics, as I show you by an example. So the question is, do we get by inductive generalization in the social world accidental generalizations or natural laws? Does it work in the social world? In the natural world, I mean, there most people believe, yes, there are natural laws, and if we hit upon them, then we can, by inductive generalization, we can state them. But the question is, I mean, are there really the same sort of laws in the social world? Well, that is obviously not obvious whether they are or not. So, for instance, and this is of course in macroeconomics, omnipresent problem, data may suggest a functional dependence of macroeconomic variables. So you have two macroeconomic variables, and there may be a functional dependence. And then the question is that an accidental generalization that may not be projected into the future? So you may have some sort of correlation, and then the question is, can I project it into the future? So in the beginning of the COVID epidemic, it happened that the countries with left-hand drive in the traffic were more successful than the countries with right-hand drive. There was a clear correlation for the first months. Yeah, of course, obviously it must be accidental, right? There we see it immediately, but you don't see it in every case. It's not that obvious. So the question is, the alternative is it just an accidental generalization, or does the functional dependence indicate a robust causal relationship that may be projected into the future, ceteris paribus, of course, excluding contravening causal influences? So that's the question. When I have in my data a certain correlation, can I project that into the future? Can I interpret it causally? Or is it just, accidentally, and that we must be very careful to project it? Here's an example, Okun's law. I have it here, the data points, US quarterly data from 1948 to 2016. Probably all of you have seen that already. So you have a correlation there between the quarterly change in GDP growth and a quarterly change of the unemployment rate, right? And they correlate. And of course, it's also some plausibility that you say, okay, if the unemployment rate goes up, then it's plausible that also not the unemployment rate gets up, that the change of the unemployment rate is increasing, that the change of the GDP growth is also is decreasing. It makes it somehow plausible. And the point is, I mean, and many of the regularities you find in macroeconomics are of that kind. You have these data points, and then the question is that purely accidental, or is there something like a law behind that, a necessity of sorts? Right, so when people discovered in the, I think, 70s stagflation, then they were completely puzzled because that didn't fit into the regularities, and then one saw, oops, we have generalized in a way that was not admissible. So that's the question, how to interpret that, and whether we can inductively then generalize to the future. Now, this is similar with respect to economic development in general. Can we inductively gain more than accidentally existing trends, right? Whose dependence on exogenous variables is unclear. So I observe in the data a certain trend, and then the question is, I mean, this is a standard problem. Can I generalize that into the future, or is it just an accidental trend? Because accidentally an influential variable is just constant, and as soon as this variable changes, then of course the trend is gone and something else is happening. So this is a standard problem for economics, and even there, then it's even worse that we are not really sure whether there are really deep and solid laws for the economy, or whether this is all somehow, just trends and generalizations. Whereas in physics, that, I mean, many people or most people believe in the existence of natural laws. If one looks a little more closely, it's not even that is completely clear anyway. So don't worry about physics here. So this is the problem of inductivism, right? We have the problem that there is accidental generalizations and there are natural law generalizations, and the question is, do I get at one of the better ones, not the accidental ones? Okay, that's the basic problems one has to have in mind, and that doesn't go away. Now, the discussion about inductivism, also in economics partly, is somewhat confused. Yeah. No, not at this level, but I'm talking here. No. Of course, you have to take that into account. But I'm just giving you the basic idea. Measurement error is, of course, everywhere. So it's not specific for inductivism. Anyway, so the problem is, this is the basic problem that's in inductivism. And there is a problem, there's a certain confusion, and we will find it later in one of the later chapters. When scientists speak about inductivism and its problems, they usually talk about the problem, how it was discussed and is discussed in philosophy, and is called there the problem of induction. And even in high school, you may hear of the problem of induction. And the problem of induction that was described by David Hume in 1739, that is not exactly the same as the problem I have discussed here. And it's important for you to see the difference between this problem that is discussed in philosophy and the problematic aspect of induction as it appears in economics, for instance. So that's 5 more minutes or so, and then we make the break. So, in philosophy, the question is, what is the justification of inductive inference in the successful cases? So in philosophy, people say, and this is, of course, you look at the 18th century, then there's 100 years of successful physics, 120 years of successful physics, and they articulated natural laws by induction, and then the philosopher said, oh, that's nice that we have these inductive generalizations that work and they get at natural laws. But the question is, can we justify this step? Right? Can we justify that? Do we have an argument, a good argument, why it is possible to come to make these inductive generalizations? It turned out that this is awfully difficult, right? And for 200 years, most philosophers said it can't be justified, right? It doesn't work. So that's one problem. That's what the philosophers worries. Right? And it's a particular philosophical worry in the successful cases. In science, that is not the worry of the scientists. Scientists take the in-principle possibility of inductivism, of induction, for granted. That's not their problem. Their problem is, the question is usually how can we practically distinguish valid inductive inferences, whatever their justification is, from invalid ones. Right? As a scientist, you don't care. You don't say, what is the final justification of induction? You say that leave that to the philosophers. Leave me alone. I want to make good inductive inferences and then have wonderful hypotheses that I generate this way. I'm not interested in that fundamental question. And therefore, for me as a scientist, I must distinguish between the practically valid inductive inferences and distinguish them from the invalid ones. And these, of course, the invalid ones are those where we inductively generalize to an accidental generalization. Right? So you must, as a scientist, you must find out, is that what I'm generalizing to something accidental, or is it something, so to speak, in nature? And that is what you have to distinguish. If you find something where you reach something in nature, some solid natural law, so you're just happy and say, it worked, wonderful. Then only the philosopher comes say, look, what is the argument? Why does it work? And then you as a scientist say, sorry, I don't care, it works, and that's good enough for me. Right. So the problem that scientists have with inductivism or with inductive generalization is a different one than the problem that philosophers have. And very often when scientists speak about inductivism and the problem of induction, they don't see that difference, because then they read the philosopher and say, oh yes, I'm very educated now and I can tell you what the philosophical problem of inductivism is. It's not the scientific problem. Yes, please. No. They have what is complete induction. That's a completely different thing. The mathematics is very, very, very different from all the empirical sciences. That's, of course, a question then in economics, especially why do mathematical problems, which has nothing to do with reality, how can they apply it, especially when they're extremely abstract? We come to that back. But first of all, most of the things that one can discuss in philosophy of science, meaning the sciences and the empirical sciences, do not apply to mathematics. So for instance, you will see that later as well. For instance, definitions, usually in the empirical sciences, definitions play a very, very minor role. But that's absolutely not true in mathematics. They're absolutely fundamental and essential. So they're really different there. And I mean, for mathematics, practically all of what natural scientists and economists, for that matter, do cannot be distinguished from lyrics. I mean, because you don't have proof. So for a mathematician, if you state something, either you have a proof or you better shut up. Right? And everything what the science is, you never have proof in the mathematical sense. Never. only within a certain system, but for the interesting things, there are no proofs. And therefore, for mathematicians, it's just when scientists speak as lyrics, could say anything. All right, because you don't have proof, period. And it was hard for the scientists. I mean, this is what happened in the 17th century, that people realized, well, it's even later, it's only in the mid-19th century, they really finally realized in the natural sciences and social sciences, for that matter, we never get proof. We just don't get it. So we must have something else. And that started with this inductivism, where people still believed that you get certainty by induction. That was really in the 17th, 18th century. People still believed that, and only in the 19th century, people then really realized, no, we don't get certainty by induction. Anyway, so there is a deep difference there. And the so-called inductive reasoning in mathematics is completely different. This is complete induction, and that is real proof, building on the nature of the natural numbers. Anyway, if you want to know anything about induction in philosophy, there is one article that I can, it's not completely uncomplicated, but if you want to read something there, then read this article, The Problem of Induction, in the Stanford Encyclopedia of Philosophy. Okay, so this is very important to be clear that the philosophical problem of induction is different from the problem that we have when we are practicing scientists and using induction, right? And that is something which is very, very rarely appreciated. It took me years to discover that difference. So when I taught philosophy of science to scientists, I don't know when, 20 years ago or 30 years ago, then I didn't make the difference. And well, nobody complained really until I complained myself and said, wait a minute, something is wrong here. And that is really that difference. And we'll see that later in the class, not today. We'll see that economists then talking or somehow referring to the problem of induction, then they refer to the philosophical problem of induction, which is not the scientist's problem of induction. Anyway, so much to inductivism and induction. So usually inductivism, as far as I can see in economics, is not really declared as a position. But sometimes people use this talk, they say we're using inductive procedures or something like that, and therefore you should know it. But I would not know in the literature, in the recent literature, which I of course don't know everything, that there is someone saying, yes, I'm an inductivist. Right? That doesn't happen, but it does happen with the positions that I'm going to discuss now, that people declare, economists declare themselves as being deductivists, or Kuhnians or whatever. But it's comparatively rare, and I'll come back to that, to the effects of general philosophy of science in economics. So